Welcome to another session on design and machine elements. This is the thought for the today. Dream is not that which you see while sleeping, it is something that does not let you sleep. As students, your duty is to dream well, plan well, prepare for that, and study your daily lessons and reach your goals, achieve your aims. In today's lecture, we will see how to design a connecting rod. A connecting rod is used to connect a piston at the small end to the crank so that the translatory motion of the piston is converted into rotary motion of the crank. We will see how it works from a YouTube link. In this video, we can see that the piston has a number of piston rings in order to prevent the exit of gases. Now the connecting rod is engaging with the piston pin and the piston, and the big end on the left side is split in two halves. Now the cap is joining with the connecting rod, and they are connected by two bolts. So this is the construction of a connecting rod. I will come back to the PDF. Here the small end is connected to the piston by means of a piston pin. Big end is split in two halves and they are connected by two bolts. What is the force acting on the connecting rod? The force acting on the connecting rod is generated by the force acting on the piston. During the power stroke, the explosion of the gases inside the cylinder exert a force on the piston. Fp is a force exerted by the explosion of the gases on the piston. A part of it is transmitted to the connecting rod, that is Fc. For practical design, we assume the entire force on the piston is transferred to the connecting rod or they are equal. So we consider Fp equal to Fc for the design purposes. Now, how to design a connecting rod? Connecting rod is a machine member which is subjected to tensile and compressive forces. However, it can be observed that the compressive forces are much high when compared to tensile forces, much high than the tensile forces, and therefore the cross section is designed as a strut which is under tension. A part under tension is called a strut, so it is subjected to tension, that is called a strut, and Rankine's formula is used. So we have well-known equations by Rankine theory for designing a strut. When subjected to a compressive force, it can undergo buckling. The buckling can occur in both directions, in x-axis and y-axis. In x-axis, it is shown in figure 2. It can buckle, we can see in the front view. It can also buckle in the top view. So we will see how it will occur. So this is the case in which the buckling will occur in the front view. It will have a buckling in this direction, buckling about the x-axis. Here both ends can be connected as pin ends or hinged ends. However, it can also buckle in the vertical direction, which we can see in the top view. Here I will show you the top view. In the top view, it can also buckle along the y-axis as seen in this diagram, in the second diagram. It can buckle about the y-axis, In this case, the two ends can be considered as fixed ends. So the buckling can occur along x-axis and y-axis. However, it should be strong in both these cases. So buckling load, considering buckling load about x-axis, considering we are taking both ends as hinged, this is our equation. I am noting as equation A, and when it buckles about y axis, both ends are considered as fixed. This is equation B. Since it has to be equally strong in both these buckling cases, we can equate these two equations. We will get Ixx, that is area moment of inertia about x axis, is equal to 4 times Iyy. For a practical design, we take this value between 3 and 3.5. So, Ixx by Iyy is taken a value in between 3 and 3.5 for the practical design. If Ixx is greater than Iyy, buckling will occur about y axis and vice versa. Now, why do we select an I section? As we can see in this figure, we have a lot amount of material removed near the web, so it is very light. When it becomes light, its mass will reduce and it will reduce the inertia forces. So, I section is preferred due to lower weight and its lower inertia forces. Now, we will see what are the steps in design for the design of a conducting rod. First thing we have to do is that we have to find whether Ixx by Iyy falls in this range 3 to 3.5. After finding that, we need to design the section. We need to find the thickness of the section. The third and the fourth step includes the step for design of the crank pin and the piston pin, and the fifth step is to design the end cap and the thickness of the bolts. So, we have to design the bolt and the thickness of the end cap. This is a very simple step for the design of conducting rod. It is a very simple step. We have to just substitute the values as given in the data book. You should take care of all the units. Now, we will see a practical question. Design a conducting rod for an IC engine, that is internal combustion engine. Piston dia is 100 mm, stroke 190 mm, mass of reciprocating parts 2.25 kg, length of conducting rod equal to 380 mm. Further, it is given maximum speed equal to 1800 mm, 1800 rpm with possible overspeed of 2500 rpm. We need not worry about this overspeed, all that. We don't take that into our calculation. Maximum explosion pressure equal to 3.15 megapascal, and the bearing pressure at the small end and big end are given 15 megapascal and 10 megapascal. L by D equal to 1.3 and 2 at the big and small end. Density equal to 8000 kilogram per meter cube for the material. Allowable stress in the bolt equal to 60 megapascal, and in the cap it is given as 80 megapascal. Now, we will see our first step is to find Ixx by Iyy, and we have to check whether it is falling between 3 and 3.5. Now, this is our standard cross section of depth equal to 5t and breadth equal to 40 and all other thickness equal to t. We will find what is the value of Ixx and Iyy for this section. So, first we will find what is Ixx. In order to find Ixx of this section, breadth 40 and height 5t, I will consider this section initially as a rectangle which is shown in red. See the rectangle shown in red. What will be the moment of inertia about x axis? So, we know for a rectangle, moment of inertia is bh cube by 12. So, for the red rectangle, I can write Ixx equal to, for this rectangle, Ixx will be equal to, this base is 40 and height is 5t. So, base into height cube divided by 12. So, this is the full red rectangle, full area. Now we have to subtract these green areas. What will be the base of these green rectangles? Its base will be 4t minus t, that will be base will be 3t, and its height is 3t. So 3t whole cube by 12. So my total Ixx will be equal to, we have to add this one, we have to subtract this one. So 4t into 5t whole cube by 12. This is for the red rectangle, minus 3t into 3t whole cube by 12, which is for the green shaded regions of green rectangles. So I will get this value Ixx equal to 419 t raised to 4 by 12. Further, I need to find Iyy, because our aim is to find Ixx by Iyy. Now we will find what is Iyy. In order to find Iyy, I am inverting this section so that my new height will be 40 and width will be 5t. In order to find the moment of inertia of such a section, I will be dividing this section into 3 rectangles. So this is rectangle 1, rectangle 2 and rectangle 3. Rectangles 1 and 3 are similar. So what will be the moment of inertia of 1 about y, about the horizontal axis, y axis? Its moment of inertia will be bhq by 12. So its base is t and height is 4t. So its moment of inertia will be bhq by 12, t into 4t whole cube by 12. There are 2 such similar triangles, 1 and 3 are similar. So for 1 and 3 rectangles, I can take multiply by 2 plus. What is the moment of inertia of the second rectangle? For the second rectangle, I can write base is 3t and height is t, t cube by 12, bhq by 12. So my value of Iyy will be equal to 131 t raised to 4 by 12. So now I can find value of Ixx by Iyy. Ixx by Iyy equal to 419 t raised to 4 by 12. That was the value of Ixx divided by Iyy, 131 t raised to 4 by 12. That is Iyy. You will get that value equal to 3.19, and since this value is in between 3 to 3.5, the selected section can be used. So my section will be base is 40 and height is 5t. No, these values are equal to t. Okay. So this is the section. Now the only unknown in this value is t. If we can find the value of t, we can find all these dimensions. So our next step is to find the thickness of the section. How to find the thickness of the section? It is given in page 413, equation 19.3, sigma CR, that is a crippling load, crippling stress, sigma CR equal to FC by A, FC by A equal to sigma C by 1 plus K into L by K whole square. We can see each term by term. FC is the crippling load, sigma C is the allowable stress, K is a constant which can be taken either as 1 by 25,000 or 4 by 25,000. If it is not given, select this one pin connected, take this value of k, small k is the radius of gyration. Now we will find all of these values one by one. First we will find what is Fc. Fc is the crippling load. Crippling load or the buckling load. Crippling load or the buckling load. Now, how will you find Fc? We have already found that the maximum load on the conducting rod or the crippling load is the load on the piston during the power stroke. See this figure. During the power stroke, there will be high explosion of gases in the cylinder which exert a downward force on the piston. So, the piston moves downwards and the crank will rotate. The piston is having a circular area. So, area will be equal to pi by 4 into d square. So, the pressure on the piston equal to force by area equal to pi by 4 d square, or I can write F equal to pressure into area of the piston, piston area. This load is transferred to the connecting rod and that is same as Fc. Fc equal to pressure into piston area. Now, we are given the values of the pressure and the area. So, Fc equal to maximum explosion pressure, which is given 3.15 Newton per mm square multiplied by area of the piston. Area of the piston, here dia is of the piston is given as 100 mm. So, area will be pi by 4 into d square. I will get Fc equal to 24,740 Newton. So, this force is producing the buckling on the connecting rod. Now, we have to find A. A is the cross-sectional area of the connecting rod. What is the cross-sectional area? We can find the area section by section. Area of this section will be 40 multiplied by T, 40 square. This one is also having the same area. So, section 1 and section 2 will be having 40 square and the central area will be equal to 3T into 3, T, 3T square. So, total area will be equal to 2 into 40 square for section 1 and 2 plus area of the web. This section is called the web. This is for the flange, plus 3T square equal to 11T square. So, we have already found the area also. Now, sigma c is the yield strength of the material. If the material is not given, we can select a material from table 19.1 given in page 419. We have a number of materials. We can select one among these. If I am selecting carbon steel 0.25 to 0.35% carbon, low carbon steel, its yield point is 316. So, yield strength is 316. If I am assuming a factor of safety equal to 6, my value of sigma c will be equal to 316 divided by factor of safety equal to 6 equal to 52.6 Newton per mm square. So, I got the value of sigma c also. It completes all the numerators. We will assume k equal to 4 by 25,000, assuming both ends are connected by pins in page 416. Further, length of the connecting rod is given in the question, L equal to 380 mm. Now, the only value is radius of gyration. Radius of gyration k, which is given in, is also given in table 1.3, a page 12. or I can write K equal to root of Ixx by A equal to, if you are remembering, Ixx was equal to 419 T raised to 4 by 12 divided by A is the area cross section 11 T square. After substitution, I will get K equal to 1.78 T. So, if you have all these values, we will substitute each values. So, area equal to 11 T square, area cross section. Fc was the crippling load or the force on the contained rod, 24,740 Newton. Sigma C is the material design stress, 316 by 6 equal to by factor of safety, sigma y by factor of safety equal to, which we have found from the table. I can write this value 52.6 Newton per mm square. K I will assume as 4 by 25,000, assuming pin ends. Further, I can write L equal to length of the contained rod equal to 380 mm, which is given detail, and K equal to root of I by A, Ixx by A equal to 1.78 T. After substitution, I will get thickness T equal to, I will get an equation in 4th degree power of T raised to 4. So, I will write that equation also, 52.6 by 1 plus 7.27 by T square equal to 2249 by T square. My T square will be equal to 49.08 millimeter square. T will be somewhere around 7 mm. T equal to 7 mm. After finding the value of T, I can now find the value of base 4T and 5T. Just the drawing of 4T equal to 28 mm, and the total height was equal to 5T. 5T equal to 35 mm. So, we have found all the dimensions of the cross section of the piston. Now, we will find the dimensions of the pin at the small end and the big end. First, we will consider the small end. When the force on the contained rod is transferred through the bearing to the pin at the piston and the crank ends, it is having a circular area. So, the force on the connecting rod, when it is subjected to buckling load, the force on the connecting rod is transferred to the pin. Yes, we can see the pin having a cylindrical section. Now, when the force acts not directly, it acts through the bearing. The bearing exerts a force on the pin, and pin is having a curved surface. So, force is acting in this case. So, it will have a bearing pressure. So, in such cases, bearing pressure will be equal to force by projected area. You can refer the previous sessions on fluid mechanics and strength of materials. Whenever the force acts on a curved surface, pressure equal to force by projected area. What will be the projected area of a pin? That is the area which we can see in the top view. So, that area will be a rectangular area which is shown in hatched in this figure. So, area will be equal to L into D, where L is the length of the pin which resides inside the bearing and D is the diameter of the pin. So, we can find pressure equal to force by projected area, or we can write force equal to pressure into projected area. you have to remember this equation. It's not given in the data book. So for the piston pin, I can write Fp equal to Lp. P denotes the piston pin. Lp is the length of the piston pin. Here P denotes the piston pin, and capital P denotes the pressure. So Fp equal to Lp into dP into pressure. So this is the projected area. And this is the bearing pressure. How will you find the left side? Fp is the force acting on the piston. So Fp equal to piston area into explosion pressure. We have already found this value, 24,740 Newton. Now what about Lp and dP? It is given the ratio Lp by dP equal to 2 at the small end or the piston end. Given Lp by dP equal to 2, it's a given detail at the small end, given at small end or the piston end. So I can write Lp equal to 2 dP. Lp equal to 2 dP. I will rewrite this equation. So 24,740, that is Fp equal to 2 dP square. Substituting Lp equal to Lp by dP equal to 2. From this equation, Lp equal to 2 dP into bearing pressure was given as 15 Newton per mm square. I will get dP equal to 28.71 mm. Further, Lp equal to 2 dP equal to 57.4 mm. So this completes our third step. Very simple. Now find dimensions of the big end crank pin. We have the same equation, similar equation. Fc is the force on the crank pin. Force on the crank pin and the force on the piston pin, both are same. That value is given as 24,740 Newton, because the piston, we have the piston in here like this. This force on the piston pin. We have the force on the crank pin, both are same. Force on piston pin, that same force will be force acting on the crank pin also. Crank pin. So Fc and Fp are both the same. Equal to Lc into dc Pc, where given length to diameter ratio Lc by dc equal to 1.3 at crank end. At crank end or the big end, both the same is given in the question. So I can write 24,740 equal to 1.3 dc square into pressure was given as 10 Newton per mm square. So I will get the value of diameter of the crank pin. Diameter of the crank pin equal to 43.6 mm, and length of the crank pin Lc equal to 1.3 dc equal to 56.71 mm. Okay. So we have found the dimensions of the big end and small end crank pins. Now we have to design the bolt. Very simple. We have the equation in equation 19.9. Fi max, Fi is the inertia force. Maximum inertia force occurs when theta equal to 0 degree. This theta equal to 0 degree at the head and center when they are in line. 4 pi square by g into, this is our equation. We will see how it goes. 4 pi square by g, where first we will see what's g. G equal to 9.81. So our value g equal to 9.81. Then n is a speed in RPS. It is given, it is 1800 RPM. So 1800 by 60 equal to 30 RPS. Further, it is given WR is the weight of the reciprocating parts. You should be careful about the units, because here mass of the reciprocating value is given as 2.25 kilogram. So WR will be equal to 2.25 into 9.81, that much Newton. Then N1 equal to L by R, where L is the length 380 mm, and as of now we don't know the value of R. What is R? R is the crank radius. We will see how you find the crank radius. In an engine, we can see this is the value of R. Stroke is the distance between top dead center and bottom dead center. This is TDC and this BDC, and the length between these is called the stroke. And from the geometry I can write crank radius R equal to half of the stroke. Half of the stroke. Given stroke equal to 190 mm, I can write R equal to 95 mm. Now we have all this value, L by R, all these values. Now I can substitute maximum inertia force. I will get maximum inertia force equal to 9340 Newton. Now this inertia force is acting on the bolt. So it will try to pull the bolt in both sides. So it will fail. Where it can have a failure? It will have a failure at the thread section, because it is the weakest section. There are stress concentration. It will fail. It will have a crack along this section. And inside the thread, we have major dia and minor dia. We can see in this figure, see this figure, it can fail along this section, which is the weakest section. This is the narrowest section, lowest area. What will be the area? Pi by 4 into d square, where d is the minor dia. Very important. Pi by 4 d square into this area multiplied by stress equal to force. What is the force acting? Fi, inertia force. Are we given the value of sigma? Yes. In the question it is given the value of sigma equal to 60 megapascal, 60 Newton per mm square, and we have found the value of Fi equal to 9340 Newton. Can you find D? That is the root dia or the minor dia? Yes. We can find the minor dia. We can substitute in the equation. So I will rewrite that equation. Force equal to stress sigma into area pi by 4 d square, where d is the minor dia. Minor dia. Sigma is given as 60 megapascal. Fi, we have found that value 9340 Newton. I will get diameter of the bolt, minor dia of the bolt equal to 9.95 mm, and there won't be any bolt as such having a value exact equal to 9.95. So whatever value is greater than 9.95 will be safe. So we can select a standard bolt from page 140 and 141, this table 9.8. You can refer that. Here minor dia is given in, for external thread is given in column 5. So we cannot find any values in page 140. Moving to page 141, these values are given for 10 and 12 are given in page 141. When we move to that page, our required value is 9.95. So I need to select a value just higher than that. So this is unsafe. Sorry, 9.07 is unsafe, 9.85 is also unsafe. This value 10.15, this is a safer value, which is just above 9.85. So this is the optimum value. So for that, what is our values? 12 and 1.5. 12 is the major dia or the basic dia, and 1.5 is the pitch. So my specification of the bolt will be equal to M 12 by 1.5. How many bolts were used? Number of bolt equal to 2. Number of bolt equal to 2. Okay, there is a change. There is an addition in the answer. Okay, this is the area of one bolt. So multiplied by 2. Okay, and we'll get that dia. Okay. So we have found the diameter of the bolt also. Now we have to find the thickness of the end cap. See this figure. This is the end cap. When subjected to the force, inertia force and the force on the piston, it will be subjected to bending. So what is the bending equation? Sigma equal to m by z, where m is the bending moment. Now both these ends are joined by bolts. So we will see what is our equation. M equal to Fi into L3 by 6 and Tc equal to root of 6m by Lc into sigma d. There is a change in for the equation in the data book. You change as Lc. It was given as L3 in some data books. So change this value as Lc. Where what is Lc? Lc is the length of the crank pin at the big end. We have found that value Lc equal to 56.71 mm. Now we will substitute all these values. We have already found the inertia force Fi equal to 9340. Fi equal to 9340 Newton. So we have found the value of Fi. Now we have to find L3. What is L3? L3 is the distance between the bolt centers. How will you find the distance between the bolt centers? We'll see. I have a magnified view. Here the yellow region represents the crank pin. Its diameter is DC. It is surrounded by a bearing shell and a bearing, and we have two bolts at both ends. I need to find the distance L3. So from this figure, the distance L3 will be equal to DC plus 2 into these two thickness plus twice the length given in these rectangles plus bolt dia. It will give you L3, and it is given in this equation. So L3 will be equal to bearing dia DC, bearing dia DC plus 2 into thickness of the bearing shell. Thickness of the bearing shell means, which is given in green. Then the thickness of the bearing is shown in blue color. Bearing is shown in light blue color. So thickness of the is light blue color. Then bolt dia plus some allowance. Okay, we will get that value. We can take these two values all together as about 3 to 4 mm. So in this case, I will substitute L3 will be equal to DC. That value was obtained DC was equal to 43.6 mm plus 2 into thickness of the bearing shell plus thickness of the bearing. I will take both as 3 mm. So this is for the shell 3 mm plus for the bearing also as 3 mm plus bolt dia was DB was obtained as 12 mm, diameter of the bolt, dia of the bolt M12 by M1.5 plus some allowance 3 mm. So my total value will be equal to 43.6 plus 2 into 6 12 plus 12 plus 3 67 plus 3 almost equal to 70 mm. So we have found the value of L3 also. So I can write M equal to Fi into L3 by 6, M equal to Fi into L3 by 6. I will get a value almost into 99,725 Newton millimeter. Further, I can find the value of TC. TC equal to root of 6m by LC into sigma d, where LC was the length of the crank pin. I have already found that value. LC was equal to 56.71 mm. So we will find these values. TC equal to root of 6m by LC into sigma d. So we have found the value of M equal to 99,725 Newton millimeter. Length of the crank pin was 56.71 mm. Given sigma d, the design stress for the end cap as 80 Newton per mm square, I will get the thickness TC about 11 mm. TC equal to 11.44 mm. So this completes the design of the contact rod, and at the end we can draw a figure of the conductor. You can draw a rough sketch. Okay, this is the thought for the today. It wasn't raining when Noah built the ark. Now students have a doubt whether the exams will be conducted on time or not. Whether exams will be conducted on time or not, you have to study your daily lessons. You have to prepare. When you plan and prepare, you can do well in your exams. Don't wait for the university to announce the date for the exams for the studies. Do it now. If you want to study and if you want to see good success in your life, do it now. Thank you for listening. Thank you for watching. If you like this video, please give comments and like to this video. Subscribe my channel. Thank you for listening.